Hello everybody, my name is Matt Calkins, thank you for joining me. If you're watching this lecture in the nutrition curriculum, you just finished a food frequency questionnaire, specifically the DHQ-1. This lecture will go through the validation studies of that food frequency questionnaire, and we'll discuss how researchers use these data in their studies. First, as always, my disclosures. I'm an investigator in a study that utilizes continuous glucose monitors that are provided by Abbott. All studies, whether it be randomized controlled trials or cohort studies, need an exposure or the independent variable and the outcome or the dependent variable. For instance, it just snowed here, and an example of this would be the amount of snowfall in 24 hours, which would be the exposure, and the number of auto accidents, which is the outcome. For nutritional epidemiology, the exposure is typically nutrient intakes as measured from food frequency questionnaires, with the outcomes either being hard, which are things typically reported in medical records or death certificates, or soft, such as metabolic markers. Epidemiology is an incredibly important research field for medicine. Smoking was shown to be causal of lung cancer largely by epidemiological studies due to massive effect sizes. Industrial trans fats were also banned using epidemiology and animal models. Epidemiology is typically used when exposures are difficult to control, like red meat intake over the course of 20 years, or unethical, like smoking. Other terms for epidemiological studies include observational or cohort studies. In the media, you can typically recognize when data is from an epidemiological study when they use broad nutritional recommendations such as eggs are bad for you or eggs are good for you. Also, for some examples of some famous cohort studies or epidemiological studies, we have some listed here: Framingham, N. Haynes, and the Nurses' Health Study. First, to set the stage, it is worth talking about where the error in food frequency questionnaires arise. On the left is a part of the food frequency questionnaire you just completed regarding consumption of beef hamburgers and cheeseburgers. Your answers are put through a separate database to determine the macronutrient breakdown. On the right is an example of the subcomponents of a hamburger, broken down by weight. As you can see, there is a lot of variation in a hamburger that is not able to be fully evaluated by the three questions on the left alone. Additionally, there is recall bias. You have to recall an entire year's worth of eating hamburger in order to answer the question correctly, including the amount in ounces. These two components of the food frequency questionnaire are part of what makes it imprecise. Let's map out where we'll be going over the next few slides. We're going to be looking at the validation study of the DHQ food frequency questionnaire against the 24-hour food recall. That'll be the first study on the next slide. Next, we'll look at one additional study that validates both the 24-hour food recall and the food frequency questionnaire against doubly labeled water, which is the gold standard for measuring total energy expenditure. We'll talk more about that when we get to that slide. Finally, we'll look at how researchers use this data to publish research articles. One of the validation studies of the DHQ-1 compared it to two other popular food frequency questionnaires, the Block and the Willet. In this study, 1,300 subjects completed 4 24-hour food recalls. Subjects were randomized to receive either a DHQ and Block or DHQ and Willet food frequency questionnaire. We're going to focus on the 24-hour food recall and the DHQ food frequency questionnaire alone. This is the men's results from the food recalls on the left and the DHQ to the right. Note that there was a 400 kilocalorie difference between the 24-hour food recall and the DHQ food frequency questionnaire. This results in decreases in the grams of macronutrient intakes, ranging from 15 grams for protein, 30 grams for carbs, and 25 grams for fat. However, the percent of these macronutrients as kilocalories is relatively the same. It is a well-known phenomenon that food frequency questionnaires underreport caloric intake. Researchers adjust the data for this error. They normalize the DHQ energy and the macronutrients to the recall energy, which is a factor, in this case, of 15%. In other words, they multiply all of the data they collect in the food frequency questionnaire in order to normalize it to the energy of the recall. And in this case, they increase all parameters by 15%. This is called the energy adjusted macronutrient amount. An additional concern of this study was discussed in the discussion section. The authors had to exclude biologically implausible daily energy intakes of less than 800 or greater than 4,200 kcal for men. This excluded 9% of the male subjects. That is, almost 1 out of 10 male subjects were not included in the final data analysis for this paper because they had implausible energy intakes. This next table shows the Pearson correlation coefficients between the 24-hour food recall and the DHQ-1. First, let's review correlation coefficients on the far right. This is a series of graphs from Wikipedia that demonstrate correlation coefficients from 1 to 0. Correlation coefficients decrease when data points vary from a line of best fit. If there is no correlation between two variables, then they have a correlation coefficient of 0. There are no standards for good or bad correlation coefficients. A correlation coefficient of 0.8 is generally poor for a high precision field like genetics, while it is generally seen as great for a field like nutrition, where the underlying data is much more imprecise. This imprecision is well known in nutritional epidemiology and is a major limiting factor in making conclusions from these studies. So going back to the table, the top row is the unadjusted energy intake. Then they include the macronutrients for both the unadjusted energy and adjusted. This means that when they take the baseline data without manipulation, there is a 0.47 correlation between protein intake from the 24-hour food recall to the DHQ-1. When they normalize the DHQ-1 energy to the 24-hour food recall energy, this increases to 0.57. This underreporting of energy intakes by food frequency questionnaires is, again, well known in the literature, and it is relatively standard to use energy-adjusted macronutrient intake on studies that use these questionnaires. Again, these relatively low correlation coefficients are part of what keep nutritional epidemiology imprecise. It gets worse. This study correlated total energy expenditure as measured by doubly labeled water with 24-hour food recalls and a food frequency questionnaire. Doubly labeled water is the gold standard in determining somebody's total energy output per unit of time. Researchers give subjects water with isotopes of hydrogen and oxygen. They then measure these isotopes in the breath and the urine over a period of time. Using rigorous calculations, they can determine a subject's total energy output over the course of a study period. In weight-neutral subjects, meaning a subject does not gain or lose weight, this should equal the reported energy intake on either a food frequency questionnaire or a 24-hour food recall. This slide has two sets of data. The top is the total energy expenditure, or TEE, that is measured by doubly labeled water. They repeated the doubly labeled water experiment for each of the 3 different nutrition data collecting systems in case participants changed their behavior between each method. Below, we have the REI, or the reported energy intake, as collected from each of the methods below. Therefore, you expect each of the rows to be equal as the subjects were not gaining or losing weight. Instead, there is a large discrepancy in energy intake. These data are in megajoules, and a megajoule is approximately 240 kcal. Therefore, the difference between the doubly labeled water to the measured 24-hour food recall is approximately 450 kcals. Here are the graphs which show the correlations between reported energy intake by food frequency questionnaire, reported energy intake by the 24-hour food recall against the doubly labeled water total energy expenditure. In both of these cases, the Pearson correlation coefficient is an abysmal 0.06, which is practically 0. meaning zero correlation of reported energy intake as measured by either 24-hour food recall or food frequency questionnaire, and the true energy output as measured by doubly labeled water. In their conclusion, the authors noted that there was no significant relation between reported energy intake and total energy expenditure with any of the dietary assessment methods, a finding comparable with prior studies. To bring it all home, we just discussed going from the true reality of energy expenditure as measured by doubly labeled water to 24-hour food recall, which has a Pearson correlation coefficient of 0.06, essentially zero. Next, for the 24-hour food recall to the DHQ, the validation study showed a Pearson correlation coefficient of 0.49 for energy and 0.62 for fat when adjusted by energy. But also keep in mind the paper we just saw had doubly labeled water to another food frequency questionnaire that was correlated by 0.06 as well. And as a reminder, here's what a correlation of 0.4 looks like. The main takeaway from this part of the lecture is that the inputs or exposures of nutritional epidemiology are, to put it lightly, not well correlated with what a person's true exposure to nutrients are. Again, correlation coefficients of 0.6 are considered good for nutritional epidemiology, but as it does not make the actual data themselves good. It is just the best we can do with the current technology. Next, we'll have an example of how researchers may use this data. Imagine we wanted to investigate the relationship of tomato juice or vegetable juice intake in colorectal cancer. This question may look familiar as it is the first question of the DHQ1 food frequency questionnaire you just did. If we send and receive this one question to a random sample of the population, we can compare those answers to an outcome database of colorectal cancer cases. This one-to-one exposure would appropriately have a p-value of 0.05 to reach statistical significance, as we are only making one comparison. Let's look at that relationship again, but in a different form. The questions are on the left. We follow the red arrows to comparing vegetable juice to the outcome of colon cancer. If we do not meet statistical significance with vegetable juice to colon cancer in general, we can manipulate the data by breaking outcomes down into different types of colon cancer. Remember this example when we review an article that does just this. Furthermore, if none of these are significant, we can further manipulate and dredge data to investigate other types of intakes of vegetables, like whole vegetables or broccoli versus cauliflower. In fact, there are 144 questions on the DHQ1 food frequency questionnaire. This gives investigators a near infinite amount of exposures. We can look further at other foods, like processed and unprocessed meats, geometrically increasing the number of possible associations, each with a 5% chance of being associated by sheer chance alone. But we do not have to stop there. There are further databases we can plug our food frequency questionnaire data into to break it down into macro and micronutrients. Breaking this down further, we have carbohydrates, fats, proteins, antioxidants, vitamins, minerals, and many other micronutrients I cannot fit on the screen. But wait, there's more. Of carbohydrates, we can break those down into fructose, glucose, lactose. Fats, we have monounsaturated, polyunsaturated, saturated, trans. Proteins, we have the individual amino acids such as serine, leucine, arginine, di and tri-amino acids. Antioxidants, we have all of the ones that have ever been discovered, vitamins A, D, C, etc., and all of the minerals, including the trace minerals. Even worse, if we do not predefine our exposures and outcomes, we can dredge or, as Dr. Ioannidis says, torture all of our data with any outcome we could possibly think of. These amount of associations end up being difficult to comprehend. Just in this theoretical data set alone, there are 23 possible exposures and 20 possible outcomes for a total of 460 possible associations, which are all of the different colored arrows you see from the left to the right. For emphasis, let's highlight in bold where we have a 5% chance to make a type 1 or false positive error. Each time an arrow crosses the bolded red line, and we do not control for multiplicity, we have a 5% chance of a false positive. The most devious part of this entire process is that researchers do not have to tell you how many associations they have conducted before they found a good story with publishable significance. In the time it took me to make this slide, a computer could have associated hundreds of thousands of exposures and outcomes. Researchers could feign serendipity and report one exposure to one outcome with a p-value of 0.05. Frustratingly, in reality, they would not bother to mention all of the other associations that were null. While there are most likely some bad actors in epidemiology, just like there are some bad actors as physicians, the vast majority of epidemiology does not want to deceive you as the physician. These are just inherent limitations of the data that we must be aware of. Even if one epidemiological research group were to properly modify their p-values for multiplicity, many other groups are using those same data sets for different outcomes, effectively creating the same problem over the entire research network and data set. I hope you learned something about food frequency questionnaires and nutritional epidemiology from this lecture. The key points are that food frequency questionnaires are not precise or accurate, which limits them to generating hypotheses and not evidence of causality.